Hello everyone, I am Ishrat Jahan Rintu. Let me begin by introducing our CSE 427 lab project, which is about brain MRI segmentation using unit architecture. Brain tumors, especially gliomas, are very dangerous and can be life-threatening. That's why it's very important to detect them early. Right now, doctors have to segment brain tumors manually from MRI images, but this takes a lot of time and can vary from doctor to doctor. So our main goal was to build a deep learning model that can automatically find and segment tumors from MRI images. This will help doctors get results faster, more accurately, and without human bias. We used a dataset called TCGA-LGG, which stands for low grade glioma, collected from the Cancer Imaging Archive. You may ask why we focused on this. Well, gliomas are brain tumors that start slow, but they can become very dangerous if not treated early. Early diagnosis gives patients a better chance at treatment and recovery, but doing it manually is slow and tiring for radiologists. That's why we choose deep learning. It can work fast, consistently, and help reduce workload for doctors in hospitals. With this technology, we can move closer to real-time automated brain tumor detection. Uh, Now let's talk about the dataset we used. Our data came from the Cancer Imaging Archive, TCIA, and it's known as the TCGA-LGG dataset. The dataset includes MRI images of patients who have low-grade gliomas. These scans come in different formats, but we focused only on FLAIR images because they help make tumors more visible by removing background fluid signals. In total, we worked around 3,929 MRI images and their corresponding marks. The marks show which part of the brain has a tumor. All images were resized to 256 by 256 pixels for uniformity, and the marks were binary, meaning each pixel is either tumor or not. Before training the model, we had to clean and prepare the data. This is called pre-processing. First, we paired MRI image with its matching mask to make sure the model learns correctly. Then we resized both the images and marks to 256 into 256 pixels. Next, we normalize the image pixels values to a range between 0 and 1. This helps the model train more smoothly. Finally, we binarized the mask. That means we converted grayscale mask to black and white, where white represents the tumor area and black represents the normal area. These pre-processing steps help improve both the speed and the accuracy of our model during training. So with the dataset ready and pre-processed, we move on to designing and training the unit model. My teammate Nazrul Alam will now explain that part in details. Thank you.
Hello, I am SM Najmul Alam and I will talk about how we built and train our deep learning model using UNIT architecture. UNIT is a convolutional neural network especially developed for biomedical image segmentation. It has a unique encoder-decoder structure with skip connection. The encoder path captures contextual features and the decoder path reconstruct the spatial resolution to create the segmentation mask. Here out how our MRI here how's our unit works. The encoder start with 64 filters and double the number at each level. Each level uses two convolutional layers followed by ReLU activation and batch normalization. Max pooling reduces the spatial dimensions. In the decoder, we use transposed convolutional to upsample the features, gradually reconstruct the spatial size. At each step, we concentrate the upsample feature with corresponding encoder feature through skip connection. This ensures that spatial details is preserved. The final layer is 1 into 1 convolutional with sigmoid activation, which output a probability mask indicating whether a pixel belongs to the tumor class. We chose unit architecture because it can perform well even with the limited training data, which is often the case in medical dataset. and it is particularly good at detecting meditative fine gradient structure like tumor boundaries. For training, we use the ADAM optimizer with a learning rate of 10 into 10 to the power minus 4. Our loss function was dice loss, which directly optimizes for overlap between the predicted and the actual tumor region. It is especially useful in imbalance segmentation tasks where the tumor is only a small part of the image. We trained our model for 80 epochs with a batch size of 32 on NVIDIA Tesla P100 GPU. We used early stopping to halt training if validation loss didn't improve and model checkpoint to save the base model during running. So we use this parameter to evaluate our model. First of all is dice coefficient, and the second IUU and the pixel accuracy. We see the result from our training. Our dice coefficient is 0.88, and our IUU or the Jaggard index is 0.79, and our pixel accuracy is 99.8%, which is quite good. Now I will hand it over to Samira to discuss how well our model perform and what we can improve.
Thank you. I am Samira Hussain and I will be discussing our results, visual evaluations, and conclusions. Now, I will explain how well our model performed after training. We used the validation set to check the accuracy of our model. The results were quite impressive. Our model achieved a dice score of 0.88, which means it had a high overlap with the ground truth marks. The IOU score was 0.79 and the pixel accuracy reached 99.8%. These results show that our unit model learned to detect tumor regions with great precision. Especially after the 30 epoch, we saw a big improvement in segmentation performance. Now I will talk about the visual results. To understand how well the model works visually, we tested it on 20 new images that were not part of the training set. On this slide, you can see three things for each test case: the original FLAIR MRI image, the ground truth mask, the predicted mask generated by our unit model. As you can see, the predicted mask closely matched the actual tumor shapes, including irregular boundaries. Even in complex cases, our model did a good job of finding the tumor region. This visual confirmation supports our evaluation metrics. However, we faced some challenges while doing the project. Firstly, our model had difficulty uh, detecting very small tumors, especially when they looked similar to noise. Secondly, we worked only with 2D images, so the model couldn't understand the 3D structure of the tumor. And finally, we used the FLAIR modality. Other MRI types like T1 and T2 might have given better results when combined. Lastly, I want to say our unit model successfully segmented brain tumor regions from MRI scan. It reduces the manual workload for radiologists and gives fast and reliable result. But there is still room for improvement. In the future, we want to use multimodal MRI inputs like T1 and T2 along with the FLAIR. Uh, Upgrade to a 3D unit model which can learn from the full MRI volume and add post-processing techniques like CRFS to clean up the segmentation boundaries. With this improvement, our system can become more powerful and useful in the real-world hospital settings. We believe this project can serve as a foundation for real world clinical tools. Thank you for listening.